Welcome to Death by Chocolate Cookies. We're going to discuss chocolate, vanilla, the basics of doughs and what gives them their structure, and sugar. Let's get started. Despite this being called Death by Chocolate, we're going to start by talking about the other quintessential flavor, vanilla. Vanilla is one of the most popular flavorings used and is relatively expensive. It comes from the pod fruit, which many people call the bean, of an orchid from Central and South America. Shown on the right is one of the flowers along with 5 of the long fruit pods. The flavor is obtained by cutting open the pod and scraping out the seeds and pulp contained inside. Now, while the plant evolved in Central and South America, it's grown commercially in other places on the planet. However, those places lack the insects that would naturally pollinate the flower, so the pollination is done using manual labor. And since manual labor is costly, the flavor itself is relatively expensive compared to other common flavorings. Because of the relatively high cost, most vanilla flavoring consumed in the US is synthetic or imitation vanilla flavoring. It costs just a small fraction of the true vanilla extract, but is missing the broad background of chemical compounds that provides the true extract with its richer flavor. The main flavorful compound in vanilla is vanillin, shown here to the right. However, the true extract will also contain a wide variety of other compounds that give us a broad background that makes it taste better. Amongst those other compounds are lots of sugars and amino acids that can react together when heated to generate Maillard reaction, or Browning reaction, flavors. We'll talk more about Maillard reactions or Browning reactions in a future video. Vanilla extract is produced by chopping the beans and then allowing them to sit in a mixture of alcohol and water for a few days. The extract is then aged to allow time for chemical reactions between the various extracted compounds to produce an even wider variety of additional compounds, leading to a more complex flavor. This process works because vanillin and the other flavor compounds are more soluble in alcohol than in water. Remember that in an earlier video we've talked about how like dissolved like. That is, polar solutes dissolve well in polar solvents like water, and nonpolar solutes dissolve well in nonpolar solvents. The alcohol is polar, but is much less so than water. So the alcohol-water mixture will dissolve much more of the nonpolar compounds like vanillin than pure water otherwise would. Remember that we tend to combine ingredients with tastes that are complementary. Because vanilla has a fruity flavor, we typically use vanilla flavoring in sweet foods like desserts. In fact, half of the vanilla flavoring consumed in the US is via ice cream. Most of the rest goes into soda and chocolate. We tend not to add vanilla to savory dishes containing meats, but we will sometimes add it to pork or lobster dishes to broaden the flavor profile. When heated, the volatile compounds in vanilla flavoring quickly evaporate. While this is good for making your kitchen smell good, it removes these molecules from the dish, reducing the flavor once the dish is consumed. As a result, vanilla flavoring is best added near the end of the cooking process if possible. For example, if you're adding the vanilla to a lobster or pork dish you're heating in a pan, you'd want to add it just before removing the dish from the heat. Of course, for some dishes like cookies or cakes, we can't practically add the vanilla flavoring after we pull the dish out of the oven, so we're forced to add it beforehand. Let's now turn to the other major flavoring we use in desserts, chocolate. Chocolate is made from the astringent, bitter, and relatively bland seeds from a tree that evolved in the tropical South American Amazon basin. Like vanilla, the flavor is derived from the pod fruit shown here on the left growing on the tree. A dried pod is shown on the bottom right. Inside the pod is a mixture of the seeds, also called beans, and a whitish pulp. The second image shows a pod that has been cut open, the pulp removed, and the seeds placed back into the empty pod. After doing some processing, which we'll discuss in the next few slides, the beans can be ground up into a powder and eventually formed into a solid bar of chocolate. Chocolate is a pretty unique food. It's hard and dry at room temperature, but heating it up to our body temperature makes it melty and creamy. It can be sculpted into virtually any shape with either a smooth, glossy surface or a dull appearance. It's also the first truly industrial food, and I'll explain why that is in a minute. Again, the cacao tree evolved in South America and was likely spread into Central America and Mexico by people carrying the large, tough seed pods as portable energy sources, similar to how you might carry a granola bar today. But note that people at the time weren't eating chocolate in the same way that we do today. Rather, the Aztecs roasted and ground the cacao seeds and then added water to make a bitter drink that we believe was used in religious services and possibly associated with human blood. Christopher Columbus first brings cacao beans back to Europe when he returns from his fourth voyage to the Americas in 1502. Up until this point, the Mayan and Aztec people flavored their chocolate drinks with the spices that they had available to them, namely vanilla, chili, honey, and achiote, to make the bitter drink more palatable. The Europeans began adding other flavorings available to them, such as sugar, cinnamon, cloves, anise, almonds, hazelnuts, orange flower water, and musk. But the drink was still very different from the sweet hot chocolate that we might make today. The consumption of cacao slowly began to be more popular, but it was still largely for the wealthy. Making hot chocolate using milk likely arose in the late 1600s in London. Around this time, the cacao powder was also shaped into lozenges to slowly suck upon, similar to how you might use a cough lozenge today. The caffeine in the lozenge would help keep people awake, and so it became more common for soldiers to use while standing guard at night. Like the avocado we've discussed previously, the cacao bean is quite high in fat. In fact, over half the mass of the bean is fat, which we call cocoa butter. This large amount of fat made the drink very heavy and filling. In 1828, Conrad van Houten wanted to make the drink less heavy and filling. He developed a screw press that removed most of the cocoa butter, and then he sold the defatted cocoa powder. Note that the cocoa powder produced in this way contains most of the flavor from the ground bean. The cocoa butter starts out as just being a byproduct that Van Houten needs to get rid of, but it turns out to be instrumental in creating the solid chocolate that we know and love today. In 1847, cocoa butter was added to a paste of unpressed ground cocoa beans. Because the ground cocoa was unpressed, it contained all the original fat, and now even more fat, previously pressed out of a different batch, is being added. This added fat increases the fat content enough that we now have all the flavor of the cocoa powder dissolved into a framework of melty fat. And it is the first production of a solid, eating chocolate, although it's still a relatively bitter, dark chocolate. It's not until 1876 when a Swiss confectioner named Daniel Peter adds dried milk powder produced by Henry Nestle to cocoa powder to make the first solid milk chocolate. Nestle, of course, goes on to become a household name for the production of chocolate. Now, it turns out that the milk flavors blend quite well with chocolate. The sugars in the milk powder serve to dilute the strong chocolate flavor. And the milk proteins also reduce the chocolate's astringency. Remember that astringency is the dry feeling you get in your mouth after eating an unripe banana. It's caused by tannins in the unripe banana binding to the proteins in your saliva, reducing their ability to lubricate, and therefore increasing the friction in your mouth. The milk proteins bind with the tannins in the chocolate, and so there aren't any tannins left to react with the proteins in your saliva. Because most people find it more appealing than the more bitter and astringent dark chocolate, milk chocolate is the most commonly consumed form of chocolate today. But remember that I said that chocolate is the first truly industrial food. Mixing together the milk powder and ground cocoa is a labor-intensive task. It's not until 1878 that Rudolf Lindt invents the conch that this problem is resolved. A conch is a machine that uses a reciprocating ball or a cylinder to continuously mix the cacao, sugar, and milk powder together over the course of hours or days. This process breaks up the larger particles that we would otherwise feel in our mouths to produce a chocolate with the fine consistency that we're used to today. The process of making chocolate is quite complex. From the pod, the bean is rather astringent and bitter, and it has very little aroma. That is, it's not particularly tasty. It takes a good deal of processing to turn it into the more tasty and aromatic treat that we love today. Cacao beans contain two types of cells, storage cells and defensive cells. Like their name implies, the storage cells make up the majority of the cells in the bean and store the protein and fat for the seedling. The defensive cells contain the astringent phenols, anthocyanin pigments, the color, and two bitter alkaloid compounds, caffeine and theobromine. Caffeine, of course, causes a variety of changes in our bodies when we consume it. Theobromine has a very similar structure, as the only difference is that the methyl group on the top left of the structure shown below is replaced with a hydrogen atom. However, that small change changes the way that theobromine interacts with our bodies. In fact, theobromine is toxic to many mammals. Now, you don't need to worry that you'll die if you eat too much chocolate, since humans metabolize the theobromine fast enough that it's impossible to die from eating chocolate. However, many pets, such as cats and dogs, don't metabolize the theobromine nearly as quickly as humans do, and so chocolate poses a significant hazard to our furry friends, and you should not let them eat it. So after harvesting the cacao pod, farmers break open the pod, remove the beans and the pulp, and pile them up. In the ambient temperature, remember that the cacao is grown in tropical climates, microbes quickly begin growing on the sugars in the pulp. This fermentation of the beans and the pulp allow chemical reactions to generate precursors to the chocolate flavor. Depending upon conditions, this fermentation process takes a few days. Yeasts convert the sugars into alcohol and metabolize some of the acids in the pulp. As the yeasts use up the oxygen in the pile, lactic acid bacteria begin to grow. As workers then turn the pile, they reintroduce oxygen and cause acetic acid bacteria to take over. These bacteria convert the alcohol, shown on the left, into acetic acid, shown on the right. We've talked before about how an alcohol is a hydrocarbon with an OH group, a group containing one oxygen atom and one hydrogen atom. In the alcohol shown here, this group is on the right. Acetic acid, which is the major component in vinegar, is shown on the right. It's a carboxylic acid. Note, the two hydrogen atoms bound to the carbon in the molecule on the left are removed and replaced with a doubly bonded oxygen. The entire COOH group is a carboxylic acid, and this is what gives vinegar its sour taste. The acetic acid produced in the fermentation process damages some of the cells in the beans, breaking them open. The cell contents mix together with the molecules outside the cell, such as the fermentation products, and react. The astringent phenols that the plant uses as defensive chemicals will react with proteins, oxygen, and each other. This forms larger complexes that are much less astringent. That is, because they're already clumped together and they therefore can't react with the proteins in your saliva. Also, digestive enzymes in the beans break down some of the proteins and sucrose into amino acids and simpler sugars. In the roasting process, these simpler molecules are more reactive and will form a wider variety of more aromatic and tasty products. After fermentation, the beans are usually dried in the sun and then shipped to manufacturers. The manufacturers roast the beans, further developing the flavor as well as evaporating off much of the remaining acetic acid. They then grind the roasted beans, add sugar, and work the mixture to refine the flavor and texture. After the roasting process, the beans are cracked open and the nibs, the more flavorful bits on the inside, are separated from the less tasty shells. In a modern factory, the nibs are then crushed by large steel rollers into a thick fluid called cocoa liquor. The grinding process breaks open any cells not broken open during the fermentation process. This releases most of the cocoa butter, the fat that becomes the solvent. That is, the fat is the phase in which the other solute molecules are dissolved and the particles are suspended. The grinding breaks the cells into particles too small for our mouths to detect as separate gritty grains. Without this process, chocolate would have a texture similar to sandy butter. Parts of it would be creamy, but the grittiness would be quite annoying. The cocoa liquor is then treated in one of a number of different ways. If it's pressed through fine filters, the cocoa butter flows through, leaving cocoa powder behind. Alternately, if we add additional cocoa butter and sugar, we can create dark chocolate. Or we can add additional cocoa butter, sugar, and milk powder to make milk chocolate. Once the extra ingredients are added, the mixture is mixed in the conch. The friction from the continuous mixing process raises the temperature. That heat, combined with the aeration, causes many volatile compounds to evaporate. This improves the flavor as most of the volatile compounds are undesirable acids or aldehydes. The increased temperature also allows further chemical reactions to produce additional flavors, that is, the roasted, caramel, and malty flavors of pyrazines, ferraniol, and maltol. The last step in making a chocolate bar is to cool the melted chocolate to form the solid bar. However, this is surprisingly difficult to do well. In order to get stable cocoa butter crystals and a glossy, snappy chocolate rather than a dull, soft bar, manufacturers need to use a process called tempering. This involves cooling the chocolate, then rewarming it before finally cooling down to room temperature for good. Like most substances, the appearance and behavior of chocolate comes from its major component, cocoa butter. If we prepare it well, the chocolate can have a smooth and glossy, almost glassy surface that's hard and not at all greasy at room temperature. When we try to bend it, it will break with a snap, and when we heat it in our mouth, it melts and turns creamy. But if we don't prepare it well, the surface can be dull and full of grease spots. It won't be a hard, solid chunk of chocolate, but rather an almost melted mess, even at room temperature. And if we try to bend it, it won't give the satisfying snap, but rather just bend and not hold its shape. Which set of properties we get depends on how the fat molecules in the cocoa butter are arranged to form a matrix. That is, what the structure looks like on a molecular scale. The fat in cocoa butter can form 6 different types of fat crystals. 2 of these are stable and produce the glossy, dry, hard chocolate that we like. The other 4 types of crystal structures produce a looser, less organized matrix with more liquid fat, which causes a greasy, soft chocolate. The tempering process requires a few steps. First, all the fat crystals need to be melted. Then, we need to form starter crystals by cooling the chocolate somewhat. However, this will produce all 6 types of crystals, and we only want the 2 most stable crystal structures. So we need to carefully heat the chocolate back up above the melting point of the 4 less stable crystal structures without also melting the 2 more stable structures. Once all the less stable crystals are completely melted, we can then slowly cool the chocolate. By cooling slowly, we allow already existing solid crystals to grow. In this way, the liquid chocolate solidifies by joining the pre-existing, more stable crystals without forming new crystals of the 4 less stable structures. In order to temper properly, we need to very carefully control the temperature of the chocolate to temperatures that depend upon which ingredients we've added. For example, milk chocolate will need to be cooled initially to between 80 and 82 degrees Fahrenheit, then heated to between 86 and 88 degrees Fahrenheit, before finally being cooled to room temperature. That is, the less stable crystal structures will melt at temperatures below 88 degrees Fahrenheit, whereas the 2 more stable crystal structures won't be melted until 104 to 113 degrees Fahrenheit. Now, if you allow the chocolate to melt, for example by leaving your chocolate bar on the dashboard of your car on a sunny day, it will no longer be tempered. When the chocolate cools, all 6 crystal structures will form again. So when you later handle it, it will be greasy, dull, and quite messy even if back at room temperature. You can temper it again by using the process of heating and cooling, although of course it won't have the same shape as before unless you've somehow snuck a mold out of the Hershey plant. Alright, we've talked about 2 of the flavorings we might normally put in cookies. So now let's turn to the cookie dough itself. Most dishes we make from doughs need to include lots of small bubbles to break up the dough structure and make it less dense so that we can eat it more easily. We often accomplish this by allowing the dough to rise prior to baking, although sometimes the gas bubbles are formed only during the baking process. Either way, the bubbles are primarily composed of carbon dioxide, and the process of creating the bubbles is called leavening. We have 2 types of leaveners, biological leaveners and chemical leaveners. Biological leaveners are yeasts, while chemical leaveners are either baking powder or baking soda. Now, leavening is a careful balance. Too little leavening causes the food to be flat and dense, while too much leavening causes the batter or dough to overexpand and collapse into a coarse structure with a harsh flavor. The yeasts that provide the biological leavening produce carbon dioxide as a waste product of breaking down sugars in the food. This process takes a good deal of time, typically over an hour, which is fine for thick, elastic doughs like bread, but a weak or runny batter, such as for pancakes, can't contain the carbon dioxide bubbles for that long, as the bubbles will simply rise to the surface and pop. Instead, we have to use chemical leaveners for these thinner batters. Chemical leaveners use a reaction between an acid and a base to generate water, carbon dioxide, and some other product or products that ideally we can't taste. The most common base we use as a chemical leavener is sodium bicarbonate, which we also call baking soda. When baking soda mixes with an acid, they react to produce water, carbon dioxide, and a salt in the same way that the classic volcano reaction between baking soda and vinegar does. As long as the dough or batter contains enough acid, then we don't need to add any additional acid to react with the baking soda. Sometimes, however, we do need to add additional acid. This acid can be added in a variety of ways, such as with vinegar, lemon juice, or cream of tartar. Baking powder is a complete leavener, which means that it doesn't require any additional acid or base to be added. Rather, it contains both baking soda, the base, and an acid. Once added to water, the baking soda and the acid dissolve in the water and start reacting with each other to form carbon dioxide. Now, how quickly the reaction takes place depends upon how soluble the acid is in water. A highly soluble acid will dissolve quickly, and thus the reaction between the acid and the baking soda will take place very rapidly. This will produce lots of bubbles very quickly, but the reaction will quickly run its course and gas production will stop. This means that the bubbles will no longer be produced once we put our dough into the oven. On the other hand, if the acid isn't very soluble, then the reaction will take a fairly long time at room temperature. But solubility usually increases as we increase temperature, so once the dough heats up in the oven, the bubbles will be formed. So you might think that we have to decide between a quick-acting baking powder and a slow-acting baking powder, depending on which acid we include. However, most baking powders are double-acting. That is, they contain two acids. One, which is highly soluble and reacts very quickly after mixing with water, and another which is only slightly soluble in water and reacts only once the temperature is increased during baking. Now, because acids taste sour and bases taste bitter, any acid or base left over from the leavening reactants will influence the taste of our food. So ideally, we add exactly enough of each so that they completely react and we have none left over after the reaction. However, even if we add the proper amounts of each, if we don't mix the batter or dough well enough, we will have too much acid in one portion of the batter or dough and too much base in another portion. In this case, one portion of the resulting food will taste sour and another portion will taste bitter. Furthermore, because the acid and base haven't completely reacted, the dough won't have risen nearly as much and our resulting dish will be fairly dense. Additionally, some foods contain acid-base indicators whose color is affected by the pH. For example, at high pH, chocolate turns red and blueberries turn green. So in our cookie dough, we need some bubbles of carbon dioxide, but what forms the rest of the structure of the dough that holds those bubbles in place? One important ingredient is eggs. Remember that we've discussed earlier that much of the protein in the egg is contained in the albumin, the egg white, while the energy stores are in the form of fat inside the yolk. Because eggs contain water, protein, fats, and good but not overpowering flavors, they are very versatile and tend to be included in a wide variety of different dishes. Another important property of eggs is that they allow the transformation of a runny batter into a much stiffer product. That is, eggs form an important component in the structure of many of our dishes. In fact, even without any additional ingredients at all, heating an egg causes the albumin to firm up into a semi-solid mass. Let's look at why exactly this happens. The egg starts out quite liquidy because both the yolk and the white are essentially bags of water containing a variety of other molecules, including proteins. Now, proteins are very large molecules made up of hundreds or thousands of atoms. Where I can show you the chemical formula of carbon dioxide as CO2 or the chemical formula of water as H2O, I can't show you the chemical formula of a protein. Now that doesn't mean that we don't know how many carbon, hydrogen, or oxygen atoms and so on are in the protein. Rather, I mean that the chemical formula would be horrifically long and wouldn't convey much useful information. Again, proteins are very large molecules, but they're all composed of a single strand of different amino acids all linked together to form a long chain. That chain coils up and folds back on itself until it's bunched up into a very specific shape. The protein is held in this very specific shape due to chemical bonds that form between parts of the protein and nearby parts. We'll often represent the proteins in a way similar to that shown here in the form of thin lines, helical ribbons, and arrows. And we'll often use coloring to show how the various parts are connected in a chain. In the raw egg, the proteins are all folded up and have a negative charge on their outer surfaces. Because they all have the same negative charge, they repel each other. Between this negative charge and the water around, the proteins can move past each other without significantly interacting. But when we heat the egg, the molecules start moving faster and faster. As they bounce around, they collide with one another more often, and when they collide, they hit harder. That is, collisions are more frequent and they have more energy. Eventually, the bonds between portions of the same protein begin to break and the protein unfolds from its coiled, ball-like structure into a long chain. This unfolding process is called denaturing. At this point, the proteins are like long strings. Before heating, they're similar to the yarn balls on the left. If we shake the basket, the individual yarn balls can move past each other without tangling. But once unfolded, when we shake the basket, we'll quickly end up with a giant knot of yarn. Likewise, once the proteins unfold, they begin getting tangled up with one another, and chemical bonds form between different protein chains all along their lengths, and also to some extent at their ends. Now, there are still plenty of water molecules around, but now they can't easily move between the giant network of proteins. The entire egg is one semi-solid mass similar to jello. So in cooking, we use eggs to bond a liquid into a moist, delicate solid. If we overcook the eggs, we either get a rubbery texture as too much of the water is driven out and so many bonds form between neighboring proteins that the entire structure gets rigid, or the mixture curdles into hard, solid lumps and watery liquid. Just as we saw when cooking meat, we must carefully control the protein coagulation and therefore the temperature. Undiluted egg whites begin thickening at about 145 degrees Fahrenheit and are a tender solid by 150 degrees. At this temperature, one of the proteins in the albumin, ovotransferrin, which comprises about 12% of the protein, coagulates. It's not until about 180 degrees Fahrenheit that the most abundant protein, ovalbumin, coagulates. But remember that the egg is split into two main parts, the albumin and the yolk. The yolk begins to thicken at 150 degrees Fahrenheit and sets completely at 158 degrees Fahrenheit. If we have mixed the albumin and the yolk together, the mixture sets around 165 degrees Fahrenheit. If we mix an egg in with other ingredients, the temperature required to set the structures will increase a few degrees, but will still be well below the 212 degree Fahrenheit at which water boils. The reason for this is that the egg proteins have been diluted somewhat and will need additional energy to move around more to collide with one another and coagulate. Up until now, we've discussed protein coagulation using heat, but we can accomplish similar protein coagulation by using acid or salt. Remember that we said proteins have a negative charge on their surfaces, and acid has lots of positively charged hydrogen ions, and salt has lots of positively charged sodium ions. In either case, the positively charged ion is attracted to the negative charges on the surface of the protein, but this positive charge balances the negative charge on the protein, so the protein surface is neutrally charged and no longer repels other proteins. This has the effect of lowering the temperature at which the proteins coagulate together. However, if the proteins coagulate before they've fully denatured, that is, before they've fully unfolded, they don't get quite as tangled. The result is that the protein network in the cooked food is more flexible, and so the food is more tender. Okay, we've discussed the gas bubbles and the proteins that make up the majority of the structure of our cookie, so now let's turn to the sugar that gives our cookie that wonderful sweet taste. Let's start with some definitions. When I use the word sugars in the plural form, I mean the class of molecules that fall into the group called sugars. The scientific name for this group is saccharides, but I'll usually use the shorter term sugars. If I use the word sugar in the singular form, I'm referring to just one particular saccharide, sucrose, or table sugar. Another important term is carbohydrates. This word literally means hydrates of carbon, So carbohydrates are made up of carbon and water molecules, that is, carbon, hydrogen, and oxygen atoms. Let's define a few more terms. Mer means unit, so a monomer is 1 unit. I've shown this schematically with one blue oval. Di means 2, so a dimer is then 2 units, or 2 monomers bound together. This is then shown as 2 blue ovals stuck together. Likewise, poly means many, so a polymer is many monomers linked together. Now, I've shown this with 8 blue ovals, but in reality a polymer can have any number of units that's 3 or higher. It's not uncommon for polymers to have upwards of tens of thousands of units. Sometimes those units are arranged as I've shown here in a single long chain. Other times there's a branched structure, and so the polymer is arranged more like the branches and/or root system of a tree. Sugars are polymers made up of some number of monosaccharides. A saccharide, whether a monosaccharide, disaccharide, or polysaccharide, has a name that ends in ose, O-S-E. I've shown here a variety of different monosaccharides ranging from 4 to 7 carbon atoms in each monomer. You may recognize some of these names from the ingredient lists on some of the packaged foods that you might eat, such as xylose, fructose, glucose, or galactose. Just like a dimer was composed of 2 monomers linked together, a disaccharide is composed of 2 monosaccharides linked together. A wide variety of these are made in nature by various cells. Sucrose, which is composed of a glucose and a fructose linked together, is called table sugar and is what most people refer to when they use the term sugar. Maltose, which is made up of 2 glucose units linked together, is a product of starch hydrolysis. Note that the lysis here means to cut or to split. So starch hydrolysis is the process of splitting a starch molecule using a water molecule. In this case, the H2O gets split into a hydrogen atom that joins one portion of the starch and an OH that joins the other portion. Another common disaccharide is lactose, which is composed of a galactose unit and a glucose unit linked together. Lactose, of course, is the primary sugar in mammal milk. As you might have guessed, a polysaccharide is a sugar made up of many monosaccharides linked together. Again, there are a wide variety of polysaccharides, and I won't list them all, but a few of them are listed here. Amylose is made up of about 200 to 20,000 glucose units linked together to form a starch. Amylopectin is a highly branched set of glucose units linked together. Maltodextrin, which is added to many processed foods, is also a lot of monosaccharides linked together to form a starch. Note that when these molecules become this large, they're too big to bind to the taste receptors on our tongues, and so these molecules are largely tasteless to us. It's only the simpler, smaller sugars, such as mono and disaccharides, that we can taste. Plants use photosynthesis to make glucose. All the other sugars are then made by altering glucose into the other sugars. Now, as I've said before, simpler sugars are used by organisms to store energy for the short term, up to a few hours. If the energy is to be stored for longer than that, then the sugars are usually converted into either starches or fats. Again, the starches are long polysaccharide chains, and because they're so large, we don't taste them. Different sugars are detected by our tongues as different sweetnesses. Sucrose is used as a reference point of 100 sweetness units. Some sugars are more sweet, such as fructose at 173, and others are less sweet, such as glucose at 74 or lactose at 15. Corn syrup at 40 is a mixture of glucose and water and is thus less sweet than pure glucose was. If we change some of the glucose to fructose, however, we get high fructose corn syrup, which has a sweetness of 120. The fact that high fructose corn syrup tastes sweeter than sucrose, normal table sugar, means that a manufacturer can add less of the high fructose corn syrup than they would need to add sucrose to keep the same sweetness. This then saves them money, and so many highly processed foods use high fructose corn syrup in place of sucrose. Now, because plants produce glucose via photosynthesis, glucose can be metabolized, that is used for energy, by virtually every cell in our bodies. High levels of glucose in our blood triggers the release of insulin, which increases the rate of glucose uptake into our cells, thereby reducing the level of glucose in the blood. However, fructose isn't metabolized in every cell. Instead, it's primarily metabolized in the liver to replenish glucose stores in the form of glycogen and fatty acids. In fact, fructose appears to lower insulin levels in the blood. While scientists are still studying the effects of fructose compared to glucose, it appears that our bodies deal with fructose and glucose much differently, and that diets high in fructose predispose us to obesity. So it's probably best to limit your intake of foods high in fructose. Now, while most plants produce sucrose from the glucose they get from photosynthesis, it's not easy to purify the sucrose from most plants. It's much easier to refine if we start out with a plant that has the sucrose in a relatively high concentration. So we use sugarcane and the sugar beet. While we now get most of our sucrose from the sugar beet, which can grow in less tropical climates than sugar cane, I'm going to focus on the production of sucrose from sugar cane because that's what we historically used, and the production of sugar cane has had significant impacts upon history. Although we aren't going to focus on them since this is a science class rather than a history class. Historically, sugarcane was grown in developing countries, or those countries that used to be European colonies. The refining machinery was expensive, and so the production of sugar was separated into two steps: the crystallization of raw, unrefined sugar, and the refining into pure, white table sugar. First, the sugar cane is crushed to produce a juice, and then the water is boiled off, leaving behind sugar crystals with lots of impurities that provide a dark brown color. In the refineries, the impurities in the raw sugar are removed. First, the raw sugar crystals are redissolved into water and then recrystallized. The water carries away much of the impurities. Then activated charcoal is used to absorb most of the remaining impurities. As a result, refined table sugar is 99.85% pure sucrose. However, when you go to the store to buy sugar, you have a variety of different options to choose from. Granulated table sugar is relatively coarse crystals ranging in size from about zero point 0.3 to zero point 0.5 millimeters. This is the most common type of sugar we use. If we grind up those crystals to get particles ranging in size from 0.01 to about zero point 0.1 millimeters, we have powdered sugar. We tend to use powdered sugar when we want a smooth texture in a dish that we aren't going to heat, such as cake frosting. If we're going to heat the dish, then typically granulated sugar is sufficient, as the increased temperature increases the solubility of sugar enough to dissolve those larger sugar crystals. But in an unheated dish like frosting, the larger sugar crystals of granulated table sugar wouldn't all dissolve, and the resulting frosting would have a gritty texture similar to sand, not a pleasant eating experience. We can also buy brown sugar, which you might be tempted to think is simply unrefined sugar, but it's not. Instead, brown sugar is refined granulated table sugar to which impurities are added back in using some dark syrup or molasses from some stage in the refining process. Depending upon which stage the syrup is taken from, we can end up with a darker or lighter brown, and so we have a few different varieties of brown sugar. Now, because of the molasses coating the outside of the sugar crystals, brown sugar tends to clump together. This is especially prominent if the sugar is allowed to dry out, in which case we can rehydrate the sugar using a damp towel or piece of apple. Because of this tendency to clump, we also need to be careful to remove any air pockets when measuring the sugar by volume. Alternately, instead of measuring the sugar using volume, such as some number of cups, we could instead weigh it and measure using grams.